So this is important because what we're going to be doing is we're going to be focusing on a lab technique called titration. And a titration is a lab technique that we use to calculate the molarity of an unknown solution. So if I have something and I don't know what the molarity is, what is molarity again? Molarity is concentration, right? And molarity is measured in moles of solute over liters of solution. So the molarity is going to tell you whether something is a strong or a weak acid. If you have a large concentration of H+, you're going to have an acidic solution. If you have a large concentration of OH-, you're going to have a basic solution, right? That goes with our, H+ and our OH- from 0 to 14, right? H+ goes down as you get more basic. OH goes up as you get more basic. If I'm going this way, H+ decreases. If I'm going this way, OH- decreases. So what this technique is you have a known concentration of an acid or a base, and then we take that known concentration and we neutralize the unknown. And then by neutralizing the unknown, and I can figure out how much I use to neutralize, then I'm going to be able to determine the concentration or the molarity of my unknown acid or base. In a neutralization, there must be a 1-to-1 ratio between the moles of H+ and the moles of OH-, right? Water is HOH. Water is neutral because there's an equal amount of moles of H+ to the equal amount of moles of OH-. There's an equal amount of positive charge to an equal amount of negative charge. So the moles of H+ equals the moles of OH-. That is what neutral means. Neutral does not mean water. Water is neutral because of that equal H and OH. So if you have an equal amount of H+ and OH-, you have reached what we call the equivalence point, right? So then that for water would be a pH of 7, H+ equals an OH-. And now when your titration is complete, right, I want it to be neutralized and I want to make sure it's all the way neutralized. So we're going to push it a little further and we go that to what's called the end point. And again, like I said, this is a lab technique and we're using it to calculate. So let's take a look at the picture of our setup. This is a titration setup. This goes with the formula on table B, or sorry, not table B, table T, where Ma is molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base, right? Molarity of the acid volume. So remember, there's two places for molarity on your reference table. So let's go to table T. Okay, so table T. All right, so table T, now we're getting towards the end of the year, right? There's two places for moles, right? I can calculate moles here and I can calculate moles here. But I can also calculate molarity in two different places, right? There's the concentration molarity, but there's also this over here molarity. And you're going to use this titration formula anytime you see the following clues. You see the word titration, please. I mean, if you see this word in the question, you'd be a fool not to pick this formula. If you have an acid and a base, because look, here's the word acid, here's the word base. How do you know if you have an acid or a base? Something from table K in the question, something from table L is also in the question. Okay? If you have two molarities, if you're asking to solve for molarity and you're given another molarity, okay, or you have two volumes. Because remember, this molarity says liters of solution. That does not say volume, okay? All right, so this is what this situation is going to look like. This is a skinny tube called a burette, which is like a graduated cylinder, except for it kind of reads backwards. Instead of having the higher number at the top, this goes from 0 at the top, and let's say this is a 50 milliliters to 50 milliliters at the bottom. And this is right down here. This is a little valve, right, like a little faucet, and you can open and close it. And when you open it, you're going to get the liquid will drop out. And you can regulate the flow of the liquid by how far you open up the faucet, just like the sink in your house. or the sink in the lab. So we're going to fill this burette with a base. This is going to be a base with a known concentration. Remember, concentration is molarity. So that's MB. And we know the volume because that's what these little lines mean, right? That's why we use it. And so now in this Erlenmeyer flask, we have an acid, which this is what we don't know. This is our unknown acid. And we want to know, what is the concentration of this acid? Like, I need to know. Like, what if I found this somewhere in the lab and I needed to test it? This is how I would do it, right? There's some forensic application in here as well. This is analytical chemistry. And we're going to add an indicator, and we're going to use that phenolphthalein. And I abbreviate that PHTH. So phenolphthalein is going to go from, where do I want? I'm just going to write that over here. So PHTH. Phenolphthalein is going to go from colorless to pink. And it's going to turn pink at a pH of 8. So when I put this in here, if this is an acid, the acid is less than 7. So with the indicator, this is going to be clear. As this starts, this is why I'm choosing the colors. As I start adding this clear base, what's going to happen is you're going to start seeing little bits of pink. And then the pink will go away. My eraser's not really working, so never mind. But as you keep adding that base, what's going to happen is it's going to end up being you're going to stop just when it hits light pink. So then we're just going to stop at light pink, and then you're going to have a starting and an ending, and then you're going to subtract your two values, right? Because we have final and initial. So if we have our initial level and we have our final level, anytime you have initial, final, anything, you got to subtract those two numbers. And then we're going to use those values to calculate my unknown value of my concentration of this acid. All right, so now let's look to see, how does this look in a question? Okay, I'm just going to do this so that we can not look at the answer. Okay, so what is the concentration? Concentration is my unknown. I have HI, 0.3 liters. I've got this word neutralized, and I have another liter volume, and I have a molarity, and I have a KOH. So I have, this is an acid, this is a base. How do I know this is a base? Because it's on table L. How do I know this is an acid? Because I have hydrogen with a group 17 element. So acid, right? When I neutralize it, H will neutralize the OH, right? Acid and a base. So then when I figure out concentration is molarity. So when I need to solve for molarity, I have two different formulas. I have molarity equals moles over liters, and I have molarity of the acid, volume of the acid, equals molarity of the base, volume of the base. So how do I know which one to choose? Well, first of all, I've got two volumes. This one has two volumes. That says liters, but which is a volume, but that only has one. And then, this is moles, sorry. And do I have moles anywhere? Nope. So I need this formula because I have all but one variable in this one, and you only ever have one X. So now let's identify our variables. So they're going to be chunked together. If this is the acid and this is a volume, these are chunked together. So your volume with the acid, and then 0.6 liters of, these are chunked together, the base. So now there's my molarity and volume of the base. And so then our next step, write down the equation and substitute your numbers. Molarity of the acid, volume of the acid, molarity of the base, volume of the base. So how would this go in the lab? In the lab, in our Erlenmeyer flask, which I am going to draw a very terrible one, you're going to end up with a pink solution, and you're going to add the base and you're going to have the acid down here. You're going to have your phenolphthalein in here. You're going to add the base dropwise until it turns pink. Because when it turns pink, you've reached the end point, because I can tell that's 8, which is past the equivalence point, which would be 7. Okay, just want to throw in how this lab technique. All right, I'd like you to try the next question. I'd like you to try to identify the variables. And I'd like you to try to solve this one by pausing the video. If you're lost, just keep watching. I'm going to do it for you. Okay, of course, I'm always writing those lines. Nothing wants to work for me. Okay, so what is the concentration of hydrochloric acid? So that's molarity of the acid. And I have 50 milliliters of 0.250 KOH. What is KOH? It is a base. How do I know it is a base? It is listed on table L, right? You got to be using table K and L. If you're stuck on a question, match words, formulas, numbers to anything in your reference tables. It's going to lead you where you need to go. So molarity of the acid, volume of the acid, molarity of the base, volume of the base. How do I know I need to use this formula instead of molarity equals moles over liters? Well, I have an acid and a base. That's one clue. I've got the word neutralize. That's another clue. I'm also asking to solve for concentration, but I'm already given a concentration. So I need to use this formula. I have all of the variables but one, and when you solve, 0.625 molar. Okay, so now let's look at this one. So we have an acid. This one's just a little bit written a little bit more basically, and has an H plus. So then that is acid, right? Because that's the definition of an acid, right? H plus. So here's my molarity of the acid, right? Because these go together. And a volume of, so then volume of goes with this. So then that's my volume of the acid. What volume of a base? Question statement is always an X, the volume of the base. 0.5 molar, and here's my base ion. My base ion, solve for X. Okay, next one. If I have 50 milliliters and I have H2SO4, this one you got to be really careful. Okay, so I want you to make sure that you're carefully reading. If I have 2 H's, I have to have 2 OH's. Okay, this is good in this question. When you get into upper level chemistry, or when you get up into honors chemistry, or in honors chemistry, or maybe in SUPA Bio or AP Bio, we have to have the number of H plus and the number of OH minus. Because if we have, so then this would be a 1 and a 1. Because, for example, if I had potassium hydroxide and H3PO4, I would need 3 times the amount of OHs. I would need a 3. So then I would have a molarity of the base, volume of the base times 3, and then, 1. And then I would have molarity of the acid, volume of the acid times 3, because I have 3 H's and I have only 1 OH. And then that would take into account. But we're not asking you to do that in Regents Chem, right? But in Honors Chem, you would do that in Honors Chem. All right, so that is all for our acid-base notes for like new content notes. So on the next page, I'm going to take you through just a really quick, forgot about this stuff. Okay, table J. So any metal above hydrogen reacts with an acid. So we talked about that somewhere before, and I can't remember where. I think when we did single replacement reactions. So which one, magnesium or copper, will react with an acid? So here is table J. And anything above that hydrogen will react with an acid. And notice the ones down here at the bottom, copper, silver, and gold, right? These have value, right? So copper, silver, and gold do not react with an acid. The least reactive is gold, right? So gold is not going to corrode in an acid. And then I'm not going to go through the single replacement and double replacement. We're going to spend more time on this when we do our oxidation and reduction unit. which I call redox. So I'm going to skip that for now because we'll talk about that again later. Let's do a quick review of the Bronsted-Lowry acid and base, okay? Because I know this is tricky. Bases accept, acids donate. So in our here, we have to have an acid and a base on both sides. So let's look at number at 2, because I like this one better. So I have H2SO4, and it's going to go to SO4, right? Remember, we're finding our partners, and the partners differ by 1 hydrogen. OH and H2O are partners because they differ by 1 hydrogen. So one's an acid and one's a base on each side. So bases accept and acids donate. So if I have H2SO4, but I end with HSO4, so what happened to this H2SO4? Did it lose or gain that hydrogen? It lost it. Does that mean it accepted it or donated it? That meant this one donates. So this one is the one that donated. And so the OH goes from OH to 2 hydrogens, from 1 hydrogen to 2. Did it donate or accept? This one accepted. So then this is an accepted, the H plus. And so our partners, if this is the acid on this side, its partner on the other side is called the conjugate base. If this is the base on this side, its partner is called the conjugate acid, because these read in both directions. Because if I read this in the reverse direction, where H2O goes to OH minus, it is now the acid and it is donating. It goes back and forth. So I just wanted to throw a quick review of that in there. And then that's it for our acids and bases.